Hello, my awesome chemists. Today we are going to start chapters 22 and 23. We're going to briefly talk about both of those chapters a little bit, and both of them are about organic chemistry. So if you take first year of chemistry in college, which is Gen Chem, which is equivalent to AP Chem, at the very end, the last chapter is going to be about organic chemistry. If you continue on with the second year of chemistry in college, the whole second year is going to be organic. So usually a whole year's worth of lecture as well as labs is dedicated to organic chemistry. So let's start with what is organic chemistry and why is it important. So organic chemistry is the chemistry, which means the materials and the changes that those materials undergo, but it's specifically the chemistry of organic molecules, and organic molecule means that it contains carbons and hydrogens as well. So let's write that definition down. So it is the chemistry of carbon-containing molecules, but again, it has carbons and hydrogens in it. So CO2, for example, would not be organic, but CH4 would be. So it really has to have carbons and hydrogens. Now, why is this important? Why do we dedicate a whole year of college chemistry to organic chemistry? Well, we know about 20 million or so compounds. The vast majority of these compounds are organic compounds. And actually, the vast majority of chemists are organic chemists. The reason is because organic molecules are all around us. Our bodies are mostly made of organic molecules, which are carbon-containing molecules. Everything that we eat is organic. It's made up of carbons and hydrogens and other things. Our clothes are mostly made of organic molecules, whether they're natural like cotton or wool or synthetic like the different polymers that we have. Those are all organic. Soaps are organic. Gasoline and different fuels are organic molecules. So medicine, a lot of the medicines is organic. Not all of it, but most of it is organic. So a lot of things around us are organic. Of course, paper and wood and a variety of different things around plastics. These are all organic. So things that we eat or that we use or our own bodies are mostly organic molecules. So organic molecules, again, are very, very important. Vast majority of substances around us and therefore vast majority of chemists that work in research and in industry are organic chemists. So organic chemistry or organic molecules are divided into these groups depending on the molecule containing something called functional group. So like I said, all organic molecules are basically carbons and hydrogens. Some of them have a few oxygens or nitrogens or sulfur, but it's mostly carbon and hydrogen. So you can imagine, if we have like 19 million or 20 million organic molecules, well, they all look very similar, right? But it's these functional groups that they have that determine the functionality, which means the reactivity and the properties of those molecules. So let's define functional group. So it is an atom or a group of atoms in an organic molecule that determine the properties and reactivity of that molecule. And so therefore property and reactivity, basically the functionality, what would you use this molecule for. And so again, organic molecules are divided into these functional groups. There are probably hundreds of functional groups. We are only going to talk about 10 of them this year, but know that there's a lot more. The simplest type of organic molecules are called alkanes. So alkanes are organic molecules where you only have single bonds, so no double bonds or triple bonds or anything like that, only single bonds. Everything is saturated. Now, the word saturated means full. And the only time we talked about saturated molecules or saturated solutions actually in chemistry is when we were talking about solutions where there's solute, and if it's a saturated solution, you have as much solute as you can. This is a different context here. This is more like saturated and unsaturated fats. If you are aware of nutritional facts. So saturated in this sense, saturated means full, and in this sense we're talking about full of hydrogens. So alkanes are full of as many hydrogens as they can possibly bond to. And therefore there are no double bonds or triple bonds or anything like that. If you were to have a double bond, that would not be saturated because you could break that double bond and add more hydrogens. So when we say saturated, again, that means it's full of hydrogens. It has as many hydrogens as it can possibly hold. The general formula for an alkane is CnH2n plus 2. What that means is, let's say that I have something called propane. So propane is C3H8. We call it propane. It ends with ane because it's an alkane. And prop means 3 carbons. So propane means you have these 3 carbons, and they're all singly bonded to one another. And then it is full of as many hydrogens as it can possibly hold. So remember that carbons can have a total of 4 bonds. And so if you give each carbon 4 bonds around it, then that's as many hydrogens as I can give it. It's saturated full of hydrogens. And so if I count how many hydrogens I have for those 3 carbons, it would be 8 hydrogens, so C3H8. Notice that this follows, this formula follows this right here. So if N was the number of carbons, in this case 3, then the number of hydrogens would be 2 times N plus 2. So 2 times 3 is 6 plus 2 is 8. Let's say I have, let's say decane. Can you guess what decane is? Dec means 10, so C10. Ane means it's an alkane, so it's saturated. So let's guess how many hydrogens it would have. Well, it would be 2N plus 2. In this case, N is 10, so it would be 22, and so on. So all the carbons here have 4 bonds. So it's attached to 4 other atoms. These are not very reactive since that single bond is pretty strong. And those can be straight chains. So it could be just like 3 carbons all in a chain, or 10 carbons all in a chain, or they can be branched. So if I have 10 carbons, maybe I have like 3 and then I'm branching off. And so on. So they could be branches or they can be long chains. And typically alkanes are used for fuels. Our second functional group is called a Cyclo Alkane. And so it's an alkane, which means it has all these properties. They're all single bonds. But having a cyclo in front of it tells us that it's cyclic. Cyclic means it forms a ring. So if I were to take my propane here, which is the 3 carbons, and I were to remove this hydrogen and this hydrogen and link this carbon to form a ring, it would look like this, with these being hydrogens right here. And so the top one there is called propane. This would be called cyclopropane. Write that down, cyclo. So it's prop because it's 3 carbons, ane because it has single bonds, and it's cyclo because it's cyclic, it forms a ring. Now you'll notice that this one is not saturated. That means it does not have as many hydrogens as it can possibly have. A cycloalkane has the formula CnH2n versus an alkane is CnH2n plus 2. So we have 2 less hydrogens. The reason why we have 2 less hydrogens is because I had to remove the ending hydrogens, this one and this one here, in order to link between this carbon and the other carbon to make it into a ring. So it is not saturated, it is not full of hydrogens because I can break that ring and add a hydrogen to this carbon and a hydrogen to this carbon to make it go back to this right there. This would be called cyclobutane. So the ane tells us that it's single bonds. Bute tells us, bute means 4 in organic chemistry, so it's made up of 4 carbons. And cyclo tells us that it's a ring. So it looks like that. The uses for cyclo alkanes is that they are also used for fuels. Now, I've always said chemists are kind of lazy. They like to find shortcuts. And so when you get to big organic molecules, we kind of get tired of writing all these carbons and hydrogens. And, you know, like we talked about decane being C10H22. We don't want to draw all that. And so chemists came up with something called a line notation to express these big organic molecules into basically zigzag lines. And so if I wanted to draw if I wanted to draw propane in the line notation, it would basically be like that. So the vertices, like the ends of your lines, those represent carbons. And the lines themselves represent bonds. And if it's a single bond, it's just a line. If it's a double bond, you make it a double line. If it's a triple bond, you make it a triple line. And so this is telling us, just by drawing this here, that tells us that there's 3 carbons, 1, 2, 3, count your vertices. They are all singly bonded to each other. So those are this bond and this bond. And it is understood that each carbon has as many hydrogens as it needs. And so if you look at this carbon, it already has 1 bond to another carbon, and so it needs 3 hydrogens to make it 4. This carbon in the middle is bonded to 2 carbons, so it already has 2 bonds, so that means it has 2 hydrogens. And then this one is bonded with 1 single bond to a carbon, and so it needs 3 hydrogens. So this is a carbon with 3 hydrogens, which is this one. This is a carbon with 2 hydrogens, which is this one. And this is a carbon with 3 hydrogens, which is this one. Now what about, let's say we talked about decane. So if I wanted to draw decane, I'd say 1, 2, 3, 4, 6, 7. So again, the vertices are my carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are my 10 carbons. This is the C10H22. And again, the lines represent single bonds, and it is understood that each carbon has 4 bonds. So you count up how many bonds are drawn, and then whatever else is left would be the hydrogens that are singly bonded there. Let's look at cyclopropane in this line notation. So it would look basically like a triangle. Sorry, I can't draw very well. Again, the vertices represent the carbons, and the lines represent the single bonds. And so there would be 1, 2, 3 carbons, all singly bonded. And each of the carbons, if you look at any of those carbons, they have 2 bonds to other carbons, and so they'd have 2 hydrogens on each of them. Let's draw cyclobutane, which is this one. It would just look like a square. Again, the vertices represent carbons, lines represent single bonds. Okay, next part, it tells you how to name cyclo alkanes. Don't worry about that. We're going to learn about naming in the next video. Next are alkenes. So we have alkanes, cycloalkanes, and then alkenes. You'll notice that alkanes and alkenes are very similarly named, except there's an A in alkanes at the end of alkanes, whereas with alkenes, it's an E. So watch out. There's an alkanes with an A, alkenes with an E, alkynes with a Y. And so they're named very similarly, but they're pretty different from each other. So alkenes are organic molecules that contain just one double bond, or at least one double bond. They can contain more than one double bond. So they have at least one double bond. These are unsaturated, and the general formula for them is CnH2n. So let's stick with our example of 3 carbons so that it's prop. This is propene. So 1, 2, 3 carbons. Connect them. And because this is propene with a double with an ene, that means a double bond, I'm going to make one of these a double bond. Okay, and then I'm going to add my hydrogens. So the first carbon here has 2 bonds already, so it needs 2 more. So it has 2 hydrogens on it. The middle carbon has 3 bonds already, so it just needs 1 more to make it 4. And then the ending carbon there has 1 bond, so it needs 3 more to make it 4. And so this is propene. Again, prop means 3 carbons. Ene means that you have a double bond. So this is called propene. Because it has a double bond, it is not saturated. It is unsaturated. Because what I could do is I can break that second bond and add a hydrogen here and a hydrogen there. And so its general formula is just like the Cyclo Alkane. It is CnH2n. So without the +2 to make it an alkane. That second bond is not as strong, and so these are used as builders. What that means is they are building blocks for bigger organic molecules. So again, because that second bond is not as strong, I can break one of these bonds and make it into a single bond, and then I can add something to this carbon and something to this carbon, and so I can make bigger molecules by breaking that double bond and adding other things. And again, we're going to worry about naming later, so don't worry about that part. Next are alkynes, and so alkynes are similar to alkanes and alkenes, except they have at least 1 triple bond. And so I'm going to try to draw propyne here. So prop means 3 carbons. I'll draw propyne. So prop means 3 carbons. The yne means we have a triple bond. So let's make one of these a triple bond. And then we add our hydrogens. So the first carbon here has already 3 bonds, so we just need 1 more to make it 4. The middle carbon already has 4 bonds, so it doesn't need any hydrogens. And the last carbon has only 1 bond, so it needs 3 more to make it 4. So we put 3 hydrogens on it. And this is the structure for propyne. These are also unsaturated because you have the triple bond. So I can break these extra bonds and add more hydrogens to both of these to make it saturated. And so this one is not full of hydrogens, not saturated. The formula for an alkyne is CnH2n minus 2. So for example, let's say I want to draw pentyne. Can you guess what pent means? That means it's 5, so C5. If it's pentyne, can we figure out how many hydrogens it has? It'll be 2n minus 2. So n here is 5, so 2 times 5 is 10 minus 2 is 8. So pentyne would be C5H8. For propyne, it's C3H4. So 2 times 3 is 6 minus 2, it'll be 4. Let's draw the stick structure. We didn't draw the stick structure for alkenes or alkynes. And so if I wanted to draw the stick structure for propene, I have 3 carbons. So there's my zigzag. Remember that each of these vertices is a carbon, so there are my 3 carbons. The lines represent my bonds, but one of my bonds is a double bond, so I draw it this way. And that's all I do. If I want to draw propyne, Here are my 3 carbons. One of those bonds is a triple bond. And so there's my propyne. If I want to draw pentyne, pent means 5, so that would be my 5 carbons. We usually don't like circle those vertices. I'm just circling them for you so you can see them, so you can see the 5 carbons. But we usually don't do that. And then make one of them a triple bond. You know, there are different ways to draw this. Let's make this the triple bond, for example. All right, our next functional group is called aromatics. Aromatics are rings that have alternating double bonds. Now, when you take organic chemistry, you will know that, or learn that aromatics are rings that have alternating double bonds, but there are other criteria that they have to have in order to really call them an aromatic. We're not going to worry about that for now. We're just going to say it's a ring that has alternating double bonds. The only one aromatic molecule that you need to know of, there are many, many organic molecules that are aromatic, but the only one that you need to know of is called benzene. Benzene is pretty unique, and it's pretty cool because it's the building block for a lot of different molecules. A lot of the gasoline molecules are benzene rings with other things attached to them. In Egypt and in a lot of other countries, when we go say we're going to fill up our car, we don't say we're going to fill it up with gasoline. We actually say we're going to fill it up with benzene. We're going to put benzene in it because benzene is one of the major components of gasoline. A lot of molecules in our body, like different steroids and things like that, have benzene rings with different things bonded to those benzene rings. A lot of medicines have benzene rings with things attached to them. And once you attach things to that benzene ring, it completely changes its properties. It's not like, you know, our body's full of gasoline-like molecules. It's just the building block of a whole bunch of different molecules. So there are millions of molecules that have benzene rings in them. Attached to other things. So benzene rings are 6 carbons that have alternating double bonds. So if you look at this here, we have our 6 carbons, and it's a ring, so it's cyclic. So it's kind of like cyclohexane. Hex means 6, right? So cyclohexane, but it has alternating double bonds. So double bond, single bond, double bond, single bond, double bond, single bond. Now, these two structures are called resonances of each other. If you remember back from chapters 7 and 8, we learned about resonance structures. And so in reality, it's not really double bond and single bonds. It is a bond and a half between each of these carbons. And so one of the ways we represent benzene rings, instead of drawing both structures, is we draw a circle inside, and that kind of tells us that there's resonance. There are alternating double bonds. So this is the stick structure for benzene rings. And so you have your 6 carbons here at the vertices, and then you have this circle in the middle that shows you that they're alternating double bonds. These are used for, or they're really the starting materials of many petrochemicals. Petrochemicals are plastics, but also fuels and things like that. But like I said, there are many molecules even inside your body that have benzene rings in them. So these 5 functional groups that we've talked about so far are called hydrocarbons. Hydrocarbons mean that they only contain carbons and hydrogens in them, only carbons and hydrogens. And there are, like I said, millions of these hydrocarbons. Now we're going to take a look at some functional groups that have oxygens in them. And we're going to start with a couple that have just one oxygen in them. And the first group we're going to look at with an oxygen is called an alcohol group. So alcohols are groups where you have an oxygen in between a carbon and a hydrogen. The general formula is ROH. R in organic chemistry means a carbon group, whatever that carbon group is. So for example, Let's try to draw propanol to stick with our 3-carbon example. So prop, again, means 3 carbons. I'll write the name first. So 1, 2, 3. If it says all, that tells us that it's an alcohol. And an alcohol is where you have an oxygen in between a carbon and a hydrogen. So pick any of those carbons and put an oxygen bonded to it and a hydrogen. So you have this OH group, basically. And so here our oxygen is in between a carbon and a hydrogen. And then let's fill out our hydrogens. So this carbon has 2 bonds, so it needs 2 more bonds. This carbon has 2 bonds, so it needs 2 more bonds. And this carbon has 1 bond, so it needs 3 more. So this is propanol. Depending on where that OH group is attached, like which carbon it's attached to, we can call it 1-propanol or 2-propanol. That indicates where that OH is. But this part is what makes it an alcohol. Again, it's just an OH group. So your oxygen is between a carbon and a hydrogen. So these are used in a variety of different things. Because they are polar, that makes them soluble, whereas a lot of organic substances are not polar, and so they're not soluble in water, but these makes them soluble. So they are used as solvents. They are used as cleaners, disinfectants. So, for example, this is rubbing alcohol. Actually, rubbing alcohol has the OH on this carbon as opposed to this carbon, but it's a similar structure. So rubbing alcohol, if you look at it, it says isopropyl alcohol or isopropanol. This is what propanol is. The iso means that the oxygen is on, or the OH group is on this carbon. So it's used as a disinfectant, as a solvent. It is used as fuel. You hear about like ethanol from corn that they use as an alternative fuel. Ethane chemistry means 2 carbons, so ethanol looks like this. F means 2 carbons, all means it has an OH group in it. And so this is ethanol. Another use for ethanol, it is the alcohol that's in alcoholic drinks, has ethanol in it. And so, again, alcohols are used in a variety of different things. The more carbons you add, the more odor it has, and usually the more carbons, the worse the odor is. Usually ethanol is not too bad, propanol is not too bad, but when you get to like bigger molecules, it has a bad odor to it for most alcohols. If I wanted to draw the stick structure for these alcohols here, let's start with propanol. So there's my 3 carbons. Let me draw them a little bit better. So there are my 3 carbons, right? And then on the way that I have it here on this carbon, so this carbon, I have an OH. And so I don't draw my carbons or the hydrogens attached to the carbons, but I draw all the other atoms. So I have to draw that oxygen that's there. And so that's my oxygen. And then if the hydrogen is bonded to the oxygen, I have to show that. So you can do it like this, or you can do it like this. And so, again, the vertices, these represent... I'm so sorry, I'm missing a carbon. Let me redraw that real quick. All right, so here are my 3 carbons. Let me point those out here. There are my 3 carbons. And then that carbon is bonded to an oxygen, so my oxygen is actually here. I apologize, I drew it incorrectly. And then you could either draw your single bond hydrogen, or you can just write an OH. So draw it like that, or like this. So again, there's 1, 2, 3. So the ones that we don't show are my carbons and the hydrogens that are on the carbons, because those are understood. If there's an oxygen, you have to show that. You have to actually draw it. And if there's a hydrogen that's not on a carbon, you have to show it as well. So that's how you draw propanol. Ethanol, there's my two carbons, and then here's my OH. And so there's a carbon, there's the other carbon, and this is the bond between the carbons, and then this is the bond between the carbon and the oxygen, and then the oxygen is bonded to a hydrogen. Okay, next group is called ethers, and I'm sorry that it printed this way. I hope yours did not print this way, that it's actually together, but like all of this is together, I guess. So ethers are groups that have an oxygen, but the oxygen is between two carbons. And so the general formula for it is ROR. Again, R's mean that they are carbon groups. So if I have my oxygen between two carbon groups, it could just be one carbon for the group. It could be two carbons. It could be three carbons. It could be whatever. Let's, for fun, make it like that. Okay, so let me add my hydrogens in so that each carbon has its 4 bonds. So this molecule is called ethyl methyl ether. Again, don't worry about the names for now. We're going to learn about that in the next video. But this is telling us that it's an, oops, I did not mean to do that. I wanted to point. There we go. Ether just tells us that it's an oxygen that's in between two carbon groups. So this oxygen is in between two carbon groups. These are usually used for anesthesia and also for antifreeze. And so antifreeze smells kind of sweet. A lot of the ethers kind of smell sweet, but at the same time it's kind of toxic. And that's why anesthesiologists have to be super careful. It's one of the hardest fields to get into, is anesthesia, because you have to be very, very precise about the amount that you give to a patient because of the toxicity of these compounds that they use. Okay, the next group, and by the way, what my goal is for this lesson is for you to be able to look at a molecule and identify what type of functional group it is. That's all really I'm looking for. So, I'm hoping that you see this and say, oh, there's an oxygen between two carbon groups, so that tells me that's an ether. Okay, the next group is called ketones, and ketones are where you have an oxygen, and it's it is double bonded to a carbon. So, for example, let's stick with our 3 carbons. So 1, 2, 3. One of those carbons is double bonded to an oxygen. The oxygen is double bonded to a carbon. So let's make it a double bond and put an oxygen there. And let's fill in our hydrogens. This one also needs 3. And the middle one is good. It already has its 4 bonds because it has 2 bonds to the oxygen and then 3, 4. This is called propanone because there are 3 carbons, so prop, and then one tells us it's a ketone, which means you have a carbon double bonded to an oxygen. Now, those names that I'm giving you are IUPAC names, so they're the official names. The common name for this molecule for propanone is actually acetone. So this is the same thing as acetone. What do you use acetone for? Do you know? Well, it's an industrial solvent, and if you use nail polish, you're probably familiar with it. It's one of the ingredients in nail polish remover. It's also actually one of the ingredients in nail polish itself. If you open up nail polish, it smells just like the remover. That's because what they do is they take the nail polish, which is a solid, and they dissolve it in acetone to make it into a solution, a liquid solution. And then you put it on your nails, you paint your nails with it. And then acetone is very volatile, evaporates very fast. And so as it evaporates, the solvent itself evaporates, but the nail polish remains on your fingernails as a solid. So how do you get it out of your nails? You use that same solvent. You take some acetone, put it on there, dissolve it, and put it on the cotton. So both nail polish and nail polish remover have acetone in them as a solvent. The last thing we'll talk about with these is the stick structure here, if I wanted to draw it. My stick structure for the acetone, which is the propanol, I have my 3 carbons, right? There's 1, 2, 3, and then that middle carbon is double bonded to an oxygen. If I wanted to draw the ethyl methyl ether that I had on top here as a stick structure, I have 2 carbons and then oxygen and then another carbon. So there's 1, 2, there are my 3 carbons. And remember, the lines are not carbons, but they're bonds. All right, let's talk about 2 more functional groups, and those 2 last functional groups contain 2 oxygens, not just 1, but 2. And the first group is called carboxylic acids. I think the most common functional groups that we are aware of are carboxylic groups and alcohols. Just because you learn about them in biology a lot and you talk about them. Carboxylic acids are found in a lot of foods. Any food that tastes slightly sour, so pretty much any fruits, some vegetables, vinegar, lots and lots of foods are slightly acidic, very, very, very slightly acidic. And the more sour it tastes, the more acidic it is. And so these acidic foods contain carboxylic acids. The general formula for carboxylic acid is ROOH. Remember, R just means a carbon group. So what that is that you have this carbon. I'm going to draw a carbon here instead of the R. And then that carbon is bonded to whatever else. That circle just means something else, whatever it is. It could be hydrogens, it could be other carbons, it could be benzene ring, it could be whatever. So to make it a carboxylic acid, basically the carbon is double bonded to an oxygen. So if you look at just this part, it looks like it's a ketone, right? Ketone is when you have a double bond oxygen to a carbon. And then that same carbon is also bonded to an OH group, which makes it look like an alcohol. So a carboxylic acid is kind of a ketone and an alcohol together, basically. So that carbon is double bonded to an oxygen and also bonded to an OH. Again, found in lots and lots of foods. Let's look at an example. So I'm going to start with propanoic acid. So prop, we said, was 3 carbons. I'm going to draw my 3 carbons. And oic acid tells us that it's a carboxylic acid. What does carboxylic acid mean? That you have a carbon that is double bonded to an oxygen, and that same carbon is bonded to an OH. Let's fill in our hydrogens. So you'd need 2 hydrogens on this carbon and 3 hydrogens on this carbon. And it is this hydrogen right here that is bonded to that oxygen. That's what makes it acidic. If you remember from a couple of chapters ago when we talked about acids and bases, an acid is something that gives off H pluses in water. And so when you put carboxylic acid in water, it's this hydrogen that leaves as an H plus, and then you get a negative charge on that oxygen there. So that's why it's acidic. Another example of carboxylic acid is ethanoic acid. Ethanoic acid. I'm going to draw that for you. Eth means 2 carbons, and oic acid means it's a carboxyl group, so the carbon has a double bond O and then an OH. Let's fill in our hydrogens. Ethanoic acid is probably the most common carboxylic acid that we kind of hear about. So ethanoic is the official name, the IUPAC name. The common name for this is acetic acid. Where have you heard about acetic acid before? Acetic acid is the active ingredient in vinegar. Vinegar is only 3% acetic acid and 97% water. So it's pretty strong. Lots of these acids have a strong odor to them. And again, this is your hydrogen that makes it acidic. If I wanted to draw the stick structure for these, for this one, I have my 3 carbons, and then that third carbon is double bonded to an O, and then it also has an OH. This one right here, I have 2 carbons, and then that carbon is double bonded to an O, and then it also has OH. Last group we're going to talk about is esters. I love esters because esters smell really good. Most organic compounds actually stink. They say if it crawls, it's biochem. If it stinks, it's organic chem. If you walk into an organic chemistry lab, it smells awful. Most organic substances smell bad. For example, a lot of these acids and a lot of the alcohols smell very bad. Butanoic acid, the one with 4 carbons, that looks like this one, but with another carbon added to it, is called butanoic acid. That smells like a combination of BO and vomit and spoiled dairy all together. And so, again, most organic molecules smell bad. Esters, however, smell really, really good. All the perfumes, all the scents, all the flavorings in foods, these are because of ester molecules. If you remember at the very beginning of the year when we talked about the orange, when we peeled it, we could smell it and the mass of it went down because of the diffusion of those gaseous particles that have the smell in them. Those were the ester molecules that evaporated and went into our noses, and those smell good. Most flavorings that come naturally are actually a bunch of esters together. So what gives orange the smell of orange is actually a whole bunch of a mixture of esters together. So when they make candy or any other flavoring, what they do is they synthetically try to create these ester molecules in the lab and combine them together in a way that produces a natural flavor, or a flavor that mimics a natural flavor. So anyway, esters are groups that have 2 oxygens. They look like this. So you have a carbon group, so a carbon bonded to something else, whatever that thing is, right? This carbon is double bonded to an oxygen, so that looks like a ketone. And then that same carbon is bonded to an O, and then another carbon. And then that carbon could be bonded to something else. So where I have my circles here and here, those could just be hydrogens, or they could be other carbons, or they could be benzene rings, they could be whatever. But what makes it an ester is that you have a carbon double bonded to an O, so that looks like a ketone. You also have an oxygen in between 2 carbons that looks like an ether. So an ester looks like a ketone and an ether kind of smushed together. So here's an example of an ester. I have here 4 carbons, and then that carbon has a double bond O, and then O, and then just another 1 carbon there. Let me put in my hydrogens. So this carbon needs 3 hydrogens. This carbon's good. This one needs 2. This one needs 2. This one needs 2. This is called methyl butanoate. And again, don't worry about the naming for now. Ending with 8 tells us that it's an ester. But this is the smell of apples. If you take organic chemistry in college, almost in all colleges, they do this lab called the synthesis of isopentyl acetate. So you make something called isopentyl acetate and then you purify it. Isopentyl acetate is the smell of bananas. It kind of smells like fake bananas, actually, like the flavoring of bananas. But it's one of the staples in organic chemistry in college. So if you take it, you will probably make this ester that smells like bananas. But again, esters are in the flavorings and scents and stuff like that, and they smell very good. These are the 10 functional groups that we're going to talk about this year. There are many, many, many other functional groups, but these are just the basic ones that we're going to study for this year. I'll see you in the next video. Hope you have a wonderful rest of your day.